This research paper investigates the classification of projective hypersurfaces that admit an induced additive action with a finite number of orbits. It begins by introducing additive actions on algebraic varieties, which correspond to local algebras of dimension n+1, and describes how to construct an additive action on Pn using an n+1 dimensional local algebra A. The authors then establish an algebraic action of the additive group of M on the algebra A, leading to isomorphisms of algebraic varieties and asymptotically equal Gn asymptotically equal express M1 equals 1 plus M. The paper reviews previous studies on additive actions, including results on non-degenerate and degenerate hypersurfaces, flag varieties, and toric varieties. The main goal is to find all projective hypersurfaces admitting an induced additive action with a finite number of orbits, which corresponds to a pair A, U, where A is a local algebra with the maximal ideal M and U is a subspace in M of codimension 1 generating A as an algebra with a unit. In the context of additive actions on projective hypersurfaces with a finite number of orbits, the authors consider pairs A, U, where A is a local, n+1, dimensional algebra with maximal ideal M and U is an n1 dimensional subspace in M that generates A as an algebra with a unit. They establish a one-to-one correspondence between equivalence classes of induced additive actions on X and isomorphism classes of pairs A, U. The relationship between morbits on X and U orbits is described using the stabilizer STM pi z with respect to the maction. The authors prove that if there are finitely many U orbits in X, then the Hilbert-Samuel sequence of A is either 1, 1, 1, 1, or 1, 2, 1, 1, which is the main result of the paper. This result is proved by assuming that there is a number k is greater than or equal to 2 with dim k mk plus 1 greater than 1, which leads to a contradiction with the assumption of a finite number of U orbits on X. Here is the combined summary of pages 58. In the context of algebraic geometry, recent research has focused on additive actions on projective hypersurfaces with a finite number of orbits. The study explores the relationship between the Hilbert-Samuel sequence of an algebra A and the number of U orbits on the corresponding hypersurface X in P, A. It is shown that if there are finitely many U orbits on X, then the pair A, U must be isomorphic to either K, X, X caret n plus 1, U underscore I, or K, X, Y, X squared, Y squared, W, where U underscore I is an n1 dimensional subspace in M that generates A, and W is a two-dimensional subspace in M. The proof involves a series of propositions and lemmas, utilizing techniques from commutative algebra and geometric invariant theory. The authors examine the case when the Hilbert-Samuel sequence of A is 1, R, 1, 1, implying that A is generated by one nilpotent element, and the case when the sequence is 1, 2, 1, 1, resulting in A being isomorphic to K, X, Y, X squared, Y squared. The main theorem is then proved, stating that there are finitely many U orbits on X if and only if the pair A, U is isomorphic to one of the aforementioned pairs. The authors show that the degree of X equals I when A, U equals K, X, X caret n plus 1, U underscore I, and equals 2 when A, U equals K, X, Y, X squared, Y squared, W. Furthermore, the authors investigate the canonical homomorphism pi, a right-pointing arrow A, where A is a polynomial ring and A is an ideal. They prove that up to automorphism of A, pi, U, can be expressed in terms of a set of generators involving X and Y. The authors then apply Theorem 2 to find the equation of the corresponding hypersurface X and provide a classification of projective hypersurfaces admitting an induced additive action with a finite number of orbits. This section delves into the existing research on additive actions on projective hypersurfaces with a finite number of orbits. It draws upon foundational work by Shafarevich, 22, who explored additive actions on toric projective hypersurfaces and introduced the concept of Euler symmetric projective toric varieties. A related study by Huang and Montero, 23, demonstrated that Fano threefolds can be viewed as equivariant compactifications of the vector group. The authors build upon this foundation to investigate the interplay between additive actions and the geometry of projective hypersurfaces, focusing on the conditions under which these actions yield a finite number of orbits. This is crucial for understanding the underlying geometric structures. The authors also discuss the interplay between additive actions and the combinatorial properties of projective hypersurfaces, highlighting how the Euler symmetric property influences the orbit structure of these actions. To provide context for their investigation, the authors present their affiliations and contact information, indicating their association with various institutions. Their research lies at the intersection of algebraic geometry and additive actions, reflecting a broader interest in understanding the geometric and algebraic properties of projective hypersurfaces. The study aims to contribute to this ongoing conversation, shedding light on the intricate relationships between additive actions and the geometric structures that underlie projective hypersurfaces. By drawing on existing research and introducing novel perspectives, the authors lay the groundwork for a deeper exploration of the properties and behaviors of additive actions on projective hypersurfaces with a finite number of orbits. This research has implications for our understanding of the geometric and algebraic properties of these complex mathematical objects.